start this up. Here we go. All right. We're going to use a star that two planets are orbiting around. And so I'm going to say that, here's a star, and there are some planets orbiting around this star. So we're going to need some data about one of them and then some data about the other one. And both of these are in orbit. And there is going to be like active construction today, so I apologize. There's a lot of beating on the walls and stuff like that. Oh well. It basically is kind of like almost like a Morse code. All right. One of these planets we live on, and the other planet is not so much. This one is a lot further away, and it has a mass and a period and a, let's see, what is the let's see, a velocity. Do what? Yeah, you really don't want to try to live on the planet that's really far away. It's just really cold back there. Okay, so one of the things that we can do is if we know that both of these orbit around the same object, so we know that they have the exact same Keplerian constant. So if they're both orbiting around the same object here, we can actually set up a relation between them, and that relationship is between the period squared and the radius cubed. So I'm going to call this planet A, and I'm going to call this planet B. And the way that we set it up is that we have, you can do Mars and Earth, but the deal is that it works with any planet. So we can get an idea of what the mass of our planet is by doing some estimations. And let's say that the people living on this planet found that the mass of that planet, so I'm going to say the mass of A, is equal to 6.2 times 10 to the 25th kilograms. Okay. And they also found that using a little bit of geometry that they exist about, let's say I'm going to call it the radius of A. They're about 2.9 times 10 to the 15th meters away from that planet. I can't remember what the actual 1 AU is. I might have to refit that number. Did we actually find out what an AU was in the previous in meters? Because I thought we had it. Okay, so let's bring this in a little bit. So instead of times 10 to the 11th, why don't we call this 2.9 times 10 to the 12th? Because then that way we're at least like within reason of being close to a star. Because if it's times 10 to the 15th, that's 11, 12, 13, 14, 15. That would be like 1,000 times further away than the distance from the Earth to the Sun. So I don't know, Chief. That seems like a big deal. All right, and we also know that the time that it takes this planet to go all the way around. Yeah. My phone's going crazy. We know that the time that it takes to go all the way around is going to be, how about 418 days? Okay. Now, with this other one, there are a couple of pieces of information. The mass of B, since we don't live on the planet, it's kind of hard to get that information, so we don't know what the mass of that planet is. The radius of B, we can, let's see here. Don't really know that much about it because we don't actually live there. What was that for 418 days? 200. Okay, 36,115,200 seconds is 418 days. You can also just call that 3.6 times 10 to the, what is that? 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th seconds. Either way, if you write it as 3.6 times 10 to the 7th seconds, you're off by 115,200 seconds. That means you would be off by about a day, which is not too terribly bad. Do what? Yeah, yeah. This is not an Earth planet. This is a theoretical alien planet. So, like, if you were out in the middle of nowhere and on some star that was just like out in the middle of deep space, and you just happen to live there, like a hermit. Do what? Yeah, if you're off by a little over a day, in terms of that, we'll be off my baby like less than 1%, so not too big of a deal. The radius of the bee, we don't know, but we do know from actually observing in the night sky that the time that it takes for it to go around one revolution is not 418 days, but more like 725 days. And so we need to probably change that over into seconds. And the question is, can we actually take this and solve for the radius and the mass? And that's what we're going to do. That's what we're going to do. You're right. The masses do end up canceling out, right? Especially the mass of the satellite. So that is an interesting thing about that. Because I think, if I remember correctly, we set the forces equal to each other. So we said that it was big G, little m, big M over d squared, and then that was equal to mv squared over d. And we found out that everybody brought mass to the party. So if everybody brought mass to the party, by those masses end up canceling out. So the question is, how are we going to find the mass of B if we're canceling out the masses and it doesn't matter? So why don't we worry about the radius first? I think the radius is probably the easier one to kind of work with. What was 725 days in seconds? 60. Okay, 6.2 times 10 to the 7th, right? Seconds. That works for me. Okay. So we know that they are shared by the same Keplerian constant. So I know that if we use Kepler's third law, we can relate them to each other. So that would be T squared of A over R cubed of A is the same proportion as T squared of B compared to R cubed of B. What's up? I don't think that I do. I don't think I have any mechanical pencil lead here. Just randomly hanging out. All right. So from this point, it's plug and chug. So I'm looking at these values, and I see that the period at A is going to be 3.6 times 10 to the 7th. So that's 3.6 times 10 to the 7th seconds squared divided by the radius, which is going to be, what is that radius? 2.9 times 10 to the 12th cubed. And then on the other side, I know that the period is 6.2 times 10 to the 7th seconds squared. And the bottom part is what I'm looking for. I'm looking for the radius of B to the third power. And that will tell me how far this planet is away from the star itself. Okay? So, what? Ooh. I think cross multiplying is in order here. I think some cross multiplying is in order, right? Okay, let's do that. I'm going to cross multiply. I'm going to get this guy over here. I'm going to get this guy over here. So that's going to be r cubed b times 3.6 times 10 to the 7th squared equals 6.2 times 10 to the 7th squared times 2.9 times 10 to the 12th cubed, and then, I probably want to take this number and move it over the other side. So r cubed is going to be equal to 6.2, and we're going to just do the same thing. Most of the stuff is going to stay the same on the numerator. And then on the denominator, we're going to divide both sides by 3.6 times 10 to the 7th squared. Okay. Now, The fun part is doing this without a calculator. You could, so like the method of squares, this is multiplied by each other. So it's 6.2 squared times 10 to the 7th squared times 3.6 squared times 10 to the 7th squared. These 10 to the 7th squareds would end up canceling out. So that's going to simplify your numbers a lot. So ideally speaking, that's one way that you could do it. Then you've just got to worry about 6.2 times 2.9, okay, and then divide by 3.6. But I'd probably just throw it in the calculator. Okay, we don't have to worry about the mental maths right now because we live in a society where we have calculators everywhere. They're literally on your phones. Although I would probably use a specialized tool for the calculator and not just your phone. The TI-84 Plus is a fantastic piece of machinery designed to calculate many things that the universe has to offer you. But this $5 Walmart calculator would also beat a cell phone any day. Okay, and this will work as well too. So try that out. I'm going to need a second on what we've got. 6.2 e to the 7th squared times 2.9 times 10 to the 12th cubed, and then divide by 3.6 times 10 to the 7th, and then go ahead and do that one more time. Get a ginormously huge number, and then we're going to take that and we're going to take the cubed root of it. Y'all know how to do a cubed root in the calculator? Caret what? Caret square root? Yeah, so like if you type in the calculator like 4 times, or 4 caret 1/3 power, I'll do that. If you do 4 and then caret parentheses 1/3, that's the same thing as the cubed root of 4. So if we're having to do a cubed root here, which honestly doesn't really show up that often in math, if you have to take a cubed root of it, that's what we're going to do. You're going to take your answer whenever you're done, and you're going to raise it to the 1/3 power. So all of this stuff. I'm sorry, what? Can you pretend that it's times 2 and it's 2? I don't understand. That doesn't even make any sense to me. You got to help me out here. I'm not really sure what's going on. Yeah. Oh, okay. I get what you're saying. Unfortunately, we have this r equals gigantic mess over here on the other side that we have to take the cubed root of. So this is the one on the right side is our problem, not the one on the left side. 4.16 times 10 to the 12th. Did we get a second? 4.16 times 10 to the 12th. Uh-oh. Take the cubed root of it. So do caret 1/3. Caret 1 divided by 3. We got a second? We got a third? Sure. You don't want to calculate? You're in AP physics class and you don't want to calculate? What is this? What is what is this? What is this? Here. It's a calculator. These little $5 Walmart calculators have more calculating capacity than the entire Allied forces in World War II. Oh, if they would have had such a thing. Okay. How do there are mental operations for calculating these things that can be done very quickly and easily. Sometimes when dealing with like cubed roots, you have to look up and on like tables and stuff like that. Um, if you're calculating square roots, there is an old machine called a slide rule that you can use to calculate roots. Only the boomers know about it this day and age. Slide rules don't really get used nearly as much as they used to because they were manual ways to calculate square roots and stuff like that. Uh, but but then we all got calculators, and now they're just like ancient technology. So this radius ended up being what 4 point. times 10 to the 12th meters. Okay, that's fair. And that's what I got too, so I think we're good to go on that. So we can actually use Kepler's third law to calculate the distance away. Now, does it actually make sense? It's a feasible answer because that radius for B is a lot longer, and I dropped my B off just randomly, so I'm going to put B down here. Uh, it's a larger number than what we started off with, so that makes a lot of sense to me that this number actually does correctly work. Now, the next thing is for the mass, it's really important to note because it was already stated Kepler's laws, Kepler's laws cannot, under any circumstance, calculate mass. Okay? If they don't give it to you, that's okay. Kepler's laws cannot calculate the mass of a planet. It's because they're based on their position, and since it is a so like let me see, the best way for me to put it is if you take a brick and you drop it and you also compare that to like a small little marble, it doesn't really matter the mass of these two objects. They're both going to fall with the exact same acceleration. The mass is irrelevant. It doesn't matter. Okay, and the main reason why it does that is because it's a force field, so it's not a contact force. It's based on you don't actually have to touch the object in order for that force to actually happen. Both objects will accelerate at the same rate. So that being said, if you have an object down here that it's being attracted to, that's supposed to be like an Earth. Sorry, that looks more like a pancake. Flat Earth confirmed. So it doesn't matter which one of these fall, they're both going to fall at the exact same rate. But if you take that same object and you just throw it really fast and it goes around the Earth, the same rule applies. It doesn't matter how massive the object is. If you can get it to go that fast, it'll just go around in a circle. It doesn't matter. So that's the same concept behind it. Yeah, and so the other way to think about it is since everybody brought mass to the party, the masses just end up canceling out. So even if you knew what the mass was, there's an infinite number of other solutions that could also work because those masses don't matter. They just end up canceling out in the first place. Okay. Yeah, I am, but I'm also terrible at drawing circles. So I can draw a cube just fine. Then whenever you get to circles, that's just too fancy for me. I can't handle it anymore. Okay. Everybody good? Try another one. All right. So we're going to compare orbital velocities. So I have two objects, identical mass. This is my circle. This is object number one going around in a circle. Whee. And object number two is going to be twice as far away. So I'm going to have object number two out here, and it's going to be twice as far. So the distance from the center is twice as much. So if this one is r, then this means the second radius is going to be 2r. Okay, so second radius is twice as much. I probably needed to put that r on the other side. That was not very smart of me. Let me try again. R, 2r. There we go. Now I have 2r twice. Great. Somebody's going to be like, is that 4r? There you go. One's r, one's 2r. Okay, so using just this information, we're going to ask ourselves, how does the orbital velocity compare? Is it bigger? Is it smaller? How does the orbital velocity compare? Okay. Uh, so the closer one should have a greater velocity than the one further away? Okay. That's right. So yeah, the one that's closer would definitely have a shorter year. That's true. Um, Now, or what if these are two satellites that are like actual like man-made satellites and not necessarily like a sun? I'm not necessarily sure we want to call it a year because a year would be like for a planet. How about we say that it has a shorter revolution? Okay, so the time period that it takes to go around in a circle is going to be shorter, so that's a shorter revolution, and that's good evidence. We also tested with our rubber stopper experiment where we were swinging those rubber stoppers around our heads, that if you get closer, it's going to be going faster. So let's try and see if we can prove that this is actually true. So this is our hypothesis based on the data that we got. Our hypothesis is going to be that the short radius is faster. Let's see if we can prove that. What kind of information are we going to need? What do we need to be able to test this out? What kind of math? Okay, what information do we need? So like, okay, so orbital period. Okay, so we would need the t, right? Do we want to plug in numbers or do we want to analytically solve for this? Okay, so then that means we will need the orbital period, and the orbital period is given the variable capital T. So we could plug in any number that we wanted to there. Say that it took it 2.5 hours to go around and orbit around the Earth, then T would be 2.5 hours or 2.5 hours. Okay, so if we're solving it analytically, the orbital period is just going to be capital T. What else do we need? Okay, so we need the gravitational constant. So we've got big G. Good thing that doesn't change. It's 6.67 times 10 to the negative 11th. I'm way too lazy to write that. I'm going to call it capital G. Okay, what other information do we need? Little g, what is little g? Little g is the acceleration due to gravity on a planet, and it is only applicable when you are on the planet. Are we on the planet? Okay, so we do not need little g right now. Okay, little g would be as if you're on the surface of the planet. Okay. Do we need the mass of what? The planet? What kind of yes is that? Yeah, it's like you're waiting for my reaction. Do you need the mass of the planet? What if the planet was this big? Would it go around as fast compared to this big? Well, we actually the radius of the planet doesn't really matter as long as you're not on it. The mass of the planet is what's actually causing the pull. So since the mass of the planet is what's causing the pull, you need the mass of the planet, which we're going to call big M. Okay? If we're solving for this, we need the mass of the planet. Do we need the mass of the satellites? Okay. Mass of the satellite would be little m. So since tell you what, since that's in the gravitational formula, we'll go ahead and put it in there. Um, Something I cannot spell satellite apparently. We are going to that's a verb. We're going to satellite. There we go. It's the mass of the satellite. Yeah. Satellite. Yes, exactly. It's Italian now. Um, Fair enough. Fair enough. Okay. So what do we need to solve? Now we got to go to the physics. Okay, find velocity. Is it moving? Okay, so it is moving. Is it moving? Yes. Is it accelerating? Okay. What kind of acceleration? Okay. So that means that the centripetal acceleration is going to be equal to, there we go, v squared over r because we're going around a circle, right? So that also means that the velocity change, our delta v, is going to be equal to, when we go around the circle, do we change speed? We go around the circle, do we change speed? Keep in mind this entire chapter is called uniform circular motion. Probably not, yeah. So since we're doing uniform circular motion, the delta v is going to be 0. There's no change in speed. The acceleration is used to keep it in the circle. The acceleration that we're using here is the acceleration used to keep it inside the circle. So, okay, so what forces do we have here? There is an acceleration, so there's got to be some force. Okay, there is a force of gravitational attraction. So if I were to do a force diagram on this object up here, where should I put my force? Okay, like this, F of G. Okay, and what else should I have? Let's say that they're moving in a, what is this, counterclockwise direction. Say they're both moving counterclockwise. They do not all have to move in the same direction. They could be moving clockwise or counterclockwise, and it would work the same. Because the centripetal acceleration would still be pointing inside the circle. Like, it doesn't matter which way we're spinning around, centripetal acceleration would still point in. I'm sorry, what's up? Oh, are all of ours moving in the same direction? I believe that there is one of them that does not play by the rules. I can't. No, no, no. Mercury plays by the rules. It's one of the ones in the outer solar system. I think. Um, I think they all rotate clockwise. One of them has a rotation that is backwards. One of them rotates on its side. Like, yeah. I think it might be Uranus, yeah. We always like the scientists always call it Uranus instead of Uranus because Uranus doesn't sound like you're talking about a butthole. So, I mean, you'll hear me always say Uranus. Yeah, there are a couple of very specific rules that Pluto doesn't follow. Okay, so Venus is weird too. Okay, that's fine. The main reason why they actually go around in the same direction is an angular momentum argument, but we'll get to that later. Yeah, there's actually an angular momentum about that. Okay, that's too hot. Venus is way too hot of a planet to even think about at the moment. Like, we would have to do some serious changes. No, actually, it's the opposite. Venus has an out of control greenhouse effect. So if you dump more water on it, water is actually a greenhouse gas because it stores heat. So actually, you don't want to do that. I don't even know if there is water. I'm pretty sure, yeah, it's not fun. All right, now wait a minute. Let's go back. We're sidetracking. Now, there is another. Oh, no, I'm sorry. I'm sorry. What other forces do I need to add to this? Correct. Do not add any other forces to this. The one force that's acting on these planets is a centripetal force. That is the gravitational force that is holding it in the circle. Okay, so gravity is the centripetal force. It is an unbalanced force, so you don't have to balance it out with something else. Okay, that's like one of the hardest things to think about with that one. If gravity stopped, it would continue to move out in a tangent line from where gravity ceased to exist. So if the planet's gravity actually just like stopped, it would just go wee, object in motion stays in motion. Then it would go this way, and then it would come back into orbit with a larger radius value. Fortunately, I don't have to worry about reality changing anytime soon, so we don't have to worry about it too bad. I have no idea. Yeah, we would not. It would not be fun. That's for sure. So, so the force of gravity is equal to big G, big M, little m over r squared, right? Okay. And we also know that that's a centripetal force, so that's the same thing as little m v squared over r, right? Okay, so we're looking for the orbital velocity. and we happen to have found it. It's right here. Okay, so what we're looking at is how do these velocities compare to each other? So if one of them is r away and the other one is 2r away, what would happen to its velocity? So I think it would probably be prudent to try to solve this expression for the velocity, right? Yeah, so like we need the r to go on the other side and we need the m to go on the other side, right? Okay. So let's try that. Let's actually take that and move it over. Is the mass the same on the satellites? The answer is it doesn't matter. Uh, if you had them as M1 or M2, what happens is the mass on the bottom would end up canceling out regardless of if you had M1 or M2. Because what you're doing is you're comparing the force of gravity of the big object to the little object. We're not actually, because I mean, if you want to get really technical, there is also a force of gravity that's attracting these two as well too, but it's really small, and that starts to hurt my brain if you start dealing with multiple forces happening at the same time. I'm just going to assume that they're far enough away that that force of gravity does not matter. Okay, so I mean, if you wanted to go there, that would make things really complicated and way above our pay grade. You would never see anything like that on the AP Physics test. Um, that would be crazy. So, uh, let's solve for v. That's what I want to do. Gonna go back this way. I'm gonna move the r up to the top, so it's g m, big M, over r, because the r is gonna one of the r's is gonna cancel out, is equal to v squared. So it'd be the square root of gm over r. So the velocity is equal to the square root of g m over r. Okay. So this would be like for the first object. Okay. If Yeah, if you look for the second one, you just need to add a 2 for this radius. How much larger does that get? Eh, not 2 times. Eh, eh. I'm just going to highlight this really important function right here. This is a mathematical function. It just happens to involve a square root. Okay, so let me let me try to explain this as best I can. Um, both of the equations had g, right? Okay, both of the equations had m, right? Okay, both of the equations had a radius, right? So the only difference is that one of them has a 1 over the square root of 2. Okay, also known as the square root of 2 over 2. So does that mean that we're going slower or faster in the back? Why slower? Ah, okay. Yeah, wait, no, look, because the square root of 2 over 2 is as a decimal. It's not stupid. It's a decimal. What is it as a decimal? Actually calculate it. Like, actually form comprehension of these numbers. What is the square root of 2 over 2 as a decimal? It's a magic number. Yes, 0.707. 0.707. So, so if we go twice as far away, we get 70% speed, right? Or 0.707 times the speed itself. Okay? So the shorter radius is going to be faster, but it's not like double, it's not like twice as fast or 4 times as fast or anything that wasn't 0.707 was wrong. Okay, so like if y'all tried to pick a number that was like 2 times, 4 times, 9 times, 14 times, all of those are not correct. Okay, so if it's twice as far away, it will get 0.707 times. Uh, it'll be 30% slower, or 70% speed. Okay, does that make sense? Now, if you use a perfect square, then you can actually get a value. So if the radius becomes 9 times as large, you'd be dividing by 1 divided by the square root of 9, so it'd be 1/3 as fast. Yeah, that can happen. Okay, so it's kind of weird. Our intuition is correct, but the number that we got for it was totally not what we expected. Okay, that square root number is kind of a little bit of a problem when it comes down to things. I'm I'm really sorry. There are a lot of exponents that have to get dealt with whenever you're dealing with gravitational stuff. So squares and cubes actually make a really big difference, and we have to be able to know how to process and handle them correctly without going insane in the process. Um, let's see here. I don't think we have a tremendously large amount of time left. It's 11:06, so I think I'm going to stop there for this one.